Okay, we'll continue what we began last lecture, superposition. But we need today to understand how will I deal with an example if there is a spring. Okay? So I have to know first what's the behavior of the spring. The spring is the kind of support that is almost similar to the roller support. So the spring is almost the same as the roller support when counting the degree. So if I am, the first step is the degree of indeterminacy. What will be the degree here? So number of redundants, I have 3 redundants here. I don't know what are the redundants of the spring, but I just told you that it's the same as the roller support. So 3 and 1 will be 4. Minus 3 equations, so the degree of indeterminacy is 1. So this structure, this beam, is once statically indeterminate. Okay. There is a huge difference between both of them in the behavior. They are all only the same when I am counting the redundancies. Okay? But for the behavior, if there is this point is A and this point is called B, what about the displacement, the vertical displacement? The vertical displacement at B, is there a vertical displacement at B? This one has YD, so the vertical displacement at B equals to 0, right? And this was our condition last lecture, that the displacement at B, if I am removing the roller support, will be equal to 0. But the spring, it can be compressed, right? It can be compressed. So the vertical displacement at A does not equal to 0. So this is the main difference in the behavior of the spring support and the roller support. They are only the same when dealing with. It only has one reaction, like the roller support, which is vertical, the same like the roller support. But the behavior, they are totally different. This one, the displacement and the roller support, the vertical displacement equals to 0, but the vertical displacement at the spring does not equal to 0. Okay? So what will be the vertical displacement at the spring? I know it's not 0, but what is the equation that I can calculate it from? I think you saw this equation before. F equal K times delta. What is F? F is the force. What is delta? Delta is the displacement. And what is K? K is the stiffness. Okay? So if I need to calculate the displacement at the spring, so it will be equal to the force divided by the stiffness. Right? So I have to memorize this equation. I will use it at the end of the solution. Okay? So now, the second step. What will be the second step? Main system. What will be the main system here? I need to remove a redundant, a reaction. Okay. For the last lecture, we got, I think, 2 examples. I chose to remove whatever I want, right? Here, when you see a spring in the beam, you have to remove the spring. It's not an option. You have to remove the spring. Because if you left the spring and you chose the main system to be hinged spring, so you removed the moment at the fixed support A. If the main system is hinged spring, it will be so difficult for you in the solution. Okay? Why? Because the spring will provide a vertical displacement, so it will differ totally in the condition at the end. So I don't need to go this hard way. So please, when you see a spring, please remove it directly. So the main system here, the redundant that I will move will be the force at the spring. So the main system will be a cantilever, fixed free, with the same uniform loop. This will be the main system that I call case no. Okay. What will be the third step? Please draw bending moment M node. So I can draw the bending moment M node. I have to first calculate the reaction. So here a uniform load, it's 2 times 6, 12. So the reaction here will be 12. The moment will be 12 times 3, 36 in this direction. So let's draw the bending moment diagram, which is called M node. So here the moment is 36. Do you remember how can I draw the bending moment for a uniform distributed load? In structure 1, we used to draw the curve exactly. So we used to use 3 tangents to draw the curve, right? But here in structure 2, we don't need this accuracy. We are just even drawing without scale. So when drawing the curve, the second degree parabola on the uniform load, just calculate the moment at the beginning of the load, which is 36, and the moment at the end of the load, which is 0, and just join and draw the curve. And what will be this equal to? PL squared over 8. Okay? And this will be the bending moment diagram. What's PL squared over 8? P is 2, L is 6. Squared divided by 8, which is 9. What will be the next step? Put the moment on a conjugate beam. Put a moment on a conjugate beam. What will be the conjugate beam here? The fixed support will be free. The free will be fixed. Right? Okay. What will I calculate here? I know from the beginning when I decided to remove the redundant, I know what will I calculate, right? I remove a vertical reaction at B, so I need in case node to calculate the vertical displacement at B. So I need delta B, okay? So what is the delta? It's the moment from the conjugate beam divided by EI. Okay, so let's calculate the areas of the bending moment. How many areas I have here? I have a triangle, the dotted triangle, and then I have to subtract this parabola from the triangle. So I have 2 areas, a triangle, and then a parabola which is subtracted from the triangle, right? Let's remember from the last time, I used to divide or split the bending moment diagram in 2 main positions or 2 main points. What are these 2 main points? If there is a difference or a change in the inertia, there is not a change in the inertia here. It's 2I from the beginning to the end. So no change in the inertia. What will be the second spot or the second position I have to divide or split the bending moment diagram? The position that I remove the redundant from, or the same meaning, which will be the position that I will calculate a displacement at. So I removed at B, so I will calculate the displacement at B. So B is on the edge. So okay, so I have no splitting. It will be, as I told in the beginning, a triangle subtracting a parabola from it. Okay? What will be the area of the triangle? It will be half base times height. So half base is 6, height is 36. It's above the datum, so it will be up. Half times 6 times 36. Is it only the area or the area divided by the I factor, the inertia factor, which is 2 here? So it will be, I think, 54. Right? 54? No. 54. What about the parabola? Will it be upwards or downwards? The parabola in all cases, the parabola is downwards. If it's under the datum, so it's downwards because it's under the datum. And if it's up or above the datum, it will be subtracted. So also it will be downwards. And CG of the parabola is in the middle. Okay? What is the area of the parabola? It's 2 over 3 base times height. The base is 6 meters. The height, what is the height of the parabola? The PL square over 8, so it's 9. Divided by the inertia factor, which is 2. It will be 18, right? Do I need to calculate the reaction? Can you remember this conversation last lecture? Do I need to calculate the reaction or not? For the first example, I have to calculate the displacement in one of the points that were inside here, like inside. So I can calculate the moment either from the left or from the right. So I decide not to calculate the reactions, so I can calculate the moment from the free side. But here, I need to calculate the vertical displacement at B. What is the displacement in the deflection-wise? It's the bending moment diagram from the conjugate B. So now I need this moment. That's my target now. So that's why I have to calculate the moment at B. So let it call delta B. I need now to calculate delta B. What's delta? Be called in terms of one node. Delta, the second number is the case number. I am in case node, so the second number will be node. The first number is the redundant number. I have only one redundant, so it's 1. So it's called here in case node delta 1 node. Okay, let's calculate it. I need to calculate the moment here. So first, the 18 times is in the middle, so 18 times 3. What about the sign? The 18 times 3, it's upwards. That's negative. If it's upwards, the moment will be negative. If downwards, the moment will be positive. So what about the 18 times 2? It's a moment with the tail above. So it will be negative 18 times 3. What about the 54? 54 times, this is of the CG of the triangle, is 1/3 and 2/3. So the 6 meter will be 2 here and 4. So 54 times 4 with a positive sign. 54 times 4. Divided by EI. So delta 1 node here will be equal to positive 162 divided by EI. Here, he gave me the value of EI. Last lecture, for the 2 examples we solved, the value of EI was not given. Why the value of EI was not given the last 2 examples? And in this example, he gave me the value of EI. Anyone knows why? Okay, it will depend on the condition. What was the condition last time? The vertical, you were removing a roller support, or we were converting a fixed support to a hinged support. So we were removing the moment. So at both cases, so the displacement was equal to 0. But what about the displacement here at B? The condition at the end, at the last step. What will be the condition at B? Will it be the vertical displacement at B equal to 0? No, this is a spring. So the vertical displacement at B will not equal to 0. It will be F over K. That's why the EI value will not go away. It went away last two examples because the right-hand side of the equation was 0. So the EI went away. But in this example, the right-hand side will not equal to 0. It will be equal to a value, okay? So the EI will not go away. That's why here he gave me the value of EI, okay? Okay, what will be the next step? Please go to the main system, remove all the loads, and just put a unit load instead of the redundant you removed. Okay, so here is the main system. I can leave it. I remove the spring that have a vertical force at B, so I will put a unit vertical force at B that equals to 1 ton. Unit force. Unit means equals to 1 ton. So I am here assuming that the redundant I remove will be equal to 1 till I know what is the real value of my redundant. Okay? And then repeat all of this again. So you have to draw the bending moment diagram. So you have to calculate the reactions first. So the y here will be 1. The moment will be 1 times 6 in this direction. Okay? So the bending moment, here is 0, here is 6. No uniform load. No uniform load. Case node is for the loading. Case 1 is for the thing you missed in case node. What did I miss in case node? The support here, I didn't consider the support at B, right? But I considered only the loads. So in case 1, I will consider the remaining part that I missed in the case node. So if I took the loads here in case 1, so that means I took the load twice. Here I took the loads, so no loads here. Here I didn't consider the vertical support, so here I have to consider the vertical support. And I made an assumption that its reaction is equal to 1. It's not equal to 1. It's just an assumption. And the bending moment will be a straight line, no uniform load. Okay? This is called M1, and then I will put it on a conjugate B. Fixed 3, and the 3 will be fixed. Is there any splitting, any dividing for the bending moment areas? No, the same as the case node. So I have only here one triangle, which is downwards, because it's drawn down the datum. So it will be downwards in the 1/3 and 2/3. The area will be half. The base is 6 meters, the height is 6 meters, divided by the inertia, which is 2, so it will be equal to 9. So the reaction here will be 9, and the moment will be in this direction. 9 times 4, 36. Right? Here goes. So delta B from case 1, what will be told in numbers? I am now in case 1, so the second number will be 1. The first number is the number of the redundant. I only have one redundant, so the first number will be also 1. So it's called delta 1, 1. What is it? The moment at B. Oh, I already calculated the moment at B here, which was 36. Intentionally, it was 9 times 4 divided by EI, and the sign is negative. It's the tail is upward, so the sign is negative. So it's negative 36 divided by EI. What about the condition here? The condition always be at the point that you remove your redundant. You remove the redundant at point B. So you have to think about a condition at point B. The condition here will be the vertical displacement, right? But if it was a roller support, so the vertical displacement equals to 0. But here it's not a vertical, it's not a roller support, it's a spring. So the delta B here will not equal to 0. Okay, so what will be equal? The equation I just erased now, it's a force divided by stiffness, right? The force in the spring divided by the stiffness of the spring. He gave me the value of the stiffness of the spring. It's 20 over 3, but take care of the units. It's ton per centimeter. And all the dimensions here are in meters, so take care, okay? And what is the force? What is the Fs? What is the F spring? What's the force in the spring? It's here. It's redundant. You're redundant, right? So the equation will be delta B from case known was called delta 1 known. Delta B from case 1 was called delta 1, 1. Is this the right delta for the loading section? Did you take all the loading or part of the loading? You took all the loading. So delta 1 known, that is for the loading, is right. But delta 1, 1 was based on that the vertical reaction at the spring equals to 1 ton. It's not equal to 1. So it's equal to x. So the right value of delta 1, 1 will be delta 1, 1 multiplied by x. What about the right hand side? That it was usually equal to 0 last time. Now it's not equal to 0. It's equal to the force at the spring, which is x. The force at the spring is x divided by k spring. That's why when I put the delta 1 known, that is 162 divided by EI, and delta 1, 1 is negative 36x divided by EI equals to x divided by k spring 20 over 3, but take care, it's ton per centimeter, so I have to multiply by 100. And here I can remove the EI values each other. Last time I removed the EI because the right hand side was equal to 0. Now the EI I have to put 6,000, and here is 6,000. From here it's an equation with only one redundant, which is x, and x will be equal to positive 3.6. What does the positive mean? The positive mean that my assumption was right. I assume that it's upwards, so my assumption is right. Now I can draw the shear and the bending moment. I redraw my beam one more time. The main beam with the uniform distributed load with the intensity of 2 tons per meter. And the reaction here is now known, it's not redundant. It's 3.6 upwards. Now I can calculate all the reactions, right? So here it's 2 times 6, 12. Sigma y equals 0, so this reaction will be 8.4, 12 minus 3.6. And you can calculate the bending moment from here, and then you can draw the shear force diagram and the bending moment diagram as in structure 1. Okay, so the same requirements here, draw shear force diagram and bending moment diagram. What's new here in this example? That I have an internal hinge. This is called the compound beam. So first, I need you to solve this one first. Both of them are compound beam, but there is a main difference between both of them. Can you see the main difference between both of them? What's the difference between these two beams? Let's start with the right one, okay? How can I solve any compound beam? There were a lot of steps. The first step was, please come here at the hinge D and split the two parts of the beam. So I have now part called CD and another part called ABD. The second step was, how do I know which part is the main beam and which part is the secondary beam? Which part is the main beam that is holding, the main beam is the strongest one, that is holding the secondary beam. Okay? So here, the part CD is like this, with only one support at D at C, right? And the part ABD is like this. This have uniform load, and this also have a uniform load. Now, can you tell me which part of these two parts is holding the other part? Or, in other words, which part is the main and which part is the secondary? In other words, which part is stable, that's the main, and which part is unstable, that is the secondary, okay? Any beam with only one support, it's like a man with only one leg. Is this stable? No. So now I knew that the CD is unstable only if it can find another part that can hold it, so it will be hold on it. So this part will fall, okay? Can this part, not the part ABD, can it hold the part CD? It will only be able to hold it if it was stable, right? So is the part ABD stable? Yes, it is stable. Fix a support here and hinge a support here, so this is stable. I have only two phases for stability. If a beam with two supports, one of them is hinged and the other is roller, or it can only be with one support, but it has to be from this kind, a fixed support. Okay? So now I can know that this will be the secondary and this will be the main. So the secondary will be up because it's being held on. The main part which will be down. So I solve it like this, right? And then I have to put another leg here. So this is the ruler. I have to put one here hinged. And when calculating the reactions, which part I have to calculate the reaction first? The main or the secondary? And why? You know why? Which beam or which part I have to start with? The secondary or the main? The secondary. But you know why? No, it's like by sense. If I am putting my hands on this table, right? So I am giving the table an extra load. what are the loads on the table? The cell phone, the markers, and this sheet, and its own weight, right? When I am standing, holding my weight on the table, so I am giving an extra load for the table, right? So now I am giving an extra load for the table. So here there are extra loads, which is my weight. Can I solve the table without knowing how much loads I give to it? No. So now the table is the main beam, and I am the secondary beam. I am giving my load to the main beam, the stable part, right? So I can't solve the main beam before I know how much load will the secondary beam give to it, right? So that's why I used to calculate the secondary beam first. So here it's 2 times 2 equals to 4. So the reaction here is 2 and here is 2. What will I do with the vertical reaction at point D? I will put it, convert it on the other side on the main beam. So now when I am solving it as a superposition, when you see a compound beam with the main part and secondary part, take the effect of the secondary part. What is the effect of the secondary part? The 2 terms that you put here, okay? And then you can throw this away now. Throw it away. So my example now is this. Solve it as usual, superposition. Okay? But here, there's a big problem here. What is the problem? When I split the beam at the internal hinge, the right part, which is BC, is stable, it's fixed free, and the left part is also stable, fixed free. So how can I know which part is the main and which part is the secondary? That's the problem here, right? And when I split them like this, at the hinge, will be like this. I can't put one up and one down. There is nothing holding the other one. Both of them are strong. Both of them are stable. Both of them are main. So I can do like this. So let's see how can I deal with a compound beam with 2 main parts, not a main part. So here I knew how to deal with a compound beam with the main part and the secondary part. Again, remove the secondary part, throw it away, but before you do this, you have to take the effect. But here, when dealing with compound beam with 2 main parts, we have to deal like this now. Okay. In all ways, if there is a compound beam, what will be here in the hinge? It has to be 2 equal reactions, one up and one down. Right? So that's what I know now. Here will be a reaction that I don't know, that is called R, and in the other part it will be also R, but on the other side. Which will be up and which will be down, I don't know. You can put R here upwards and R here downwards. Okay? And then you have to solve each part individually. You have to solve each part individually. This is called BC and this is called AC. Let's calculate the degree for part AC. For part AC, what will be the degree? 3, 4, redundant, minus 3 equations, so the degree is 1. What about the degree for part BC? 3 and 1, 4, minus 3 equal 1. Right? Is this one the same like the other one? No. Yes, they are the same. Both of them, the extra reaction is equal. This is R and this is R. They have to be equal. The main concept of the compound beam, when you split the two beams and you need to get them together again. So this here I see there wasn't any R. So if there is a 10 done here, it has to be 10 here in the opposite side. 15, 15 in the opposite side. So R and R, okay? Okay, let's solve this part. Case node, case 1. And then the other part, case node and case 1. Okay? So let's start with the left part. What will be the main system? Remove R. So the main system will be fixed free. So this is the main system. Let's call case node. Okay? I remove the R. And here, the main system, remove the R. So this is the main system for the right part, and this is case node. Okay? Here, what will I calculate? I need to calculate the vertical displacement at C, because I removed a vertical reaction at C. So I need to calculate the vertical displacement here. So I have to draw the bending moment first, M node, and then put it on a conjugate beam. So first, 3 times 4 equals 12. So the moment here will be 12 times 2, which is 24. Let's draw M node. The moment here is 0. The moment here is 24. And then join and put the PL square over 8, which is 3. 4 square divided by 8 will be, I think, 6. 6. So this is M node. What about M node here? Is there any loads here? No loads, right? So no M node. M node equal 0. So what about delta 1 node? Is there any value for delta 1 node for the right hand side? No, equal 0. So there are no loads. Let's return to the left hand side. Put the moment on a conjugate beam. Fixed will be free, free will be fixed. I now need to calculate the moment here at C. What about the areas? A triangle, the same like the last example. A triangle above the datum, so it will be upwards. And the parabola, which is subtracted, so it will be downwards in the middle. Is there any split? Do I need to split the areas? The change in inertia is here at C, and the two parts are already split at C. And the part that you remove, the point that you remove your redundant at is also at C, so it's already split. So this will be half base 4 times height 24 divided by inertia, which is 2. So here it will be 24, right? Are you confused? The parabola 2 over 3 base 4, height is PL square over 8, which is 6, divided by the inertia, which is 2. I think it will be 8, right? Okay. Let's calculate the moment here and see what will be called delta 1 node. But I can't leave the same names like this. So let's name this delta 1 node and name the other one anything. Delta 1 node dash, delta 1 node star, anything you want. Delta 1 node for AC, and this is called delta 1 node for BC. But don't leave them the same name, delta 1 node and delta 1 node. Okay? Delta 1 node, which is delta at point C, which is the moment here. So it will be 8 in the middle, so times 2, and the sign is negative, plus 24 times the 2/3 of the distance, which is 4, so it will be 2.67 divided by EI. So delta 1 node here will be equal to 28, 48, yeah. Positive 48 divided by EI. And delta 1 node dash there equals to 8. Okay, so what about case 1 on the left hand side? Remove all the loads from the main system. So this is case 1. And just only put a unit load instead of the redundant you remove. You remove the vertical reaction here at C. Okay, take care. You have the decision here to say or to put the R here upwards or here. Here in case 1, you have to follow the same criteria you decided from the beginning. So you decide that the R will be upwards for the left hand side. So when you put the unit load, the X, you have to put it upwards. You don't have the choice. And when you are dealing with case 1 for the right hand side, you have to put X downwards as you decided from the beginning. So here you have the option, here you don't have the option. Okay? Okay, for the left hand side, let's draw the moment. So 1 times 4 is 4. So the moment will be 4 and 0. This is M1 plus conjugate, beam which will be free fixed. Okay? It's only one triangle down the data, so it will be downwards. Half base is 4, height is 4 divided by 2, so this will be 4. I need also to calculate delta at C. This is C. So the moment, which is called here delta 1, 1. The moment here is only 1/4, so it's negative 4 times 2/3 of the 4, which is 2.67 divided by EI. So delta 1 here will be equal to negative 10.67 divided by EI. What about the right hand side? Calculate the moment, draw moment first. So 1 times 2 is 2. So the moment will be here 2 and here equals to 0. This is called M1 dash. It's only put it on a conjugate beam as well. Free will be fixed and fixed will be free. It's only one triangle upwards, so above the data, so it will be upwards. Half base times height, so half the base is 2, the height is 2, divided by the inertia factor, which is here only 1. It's 5, so the inertia factor is 1. So it will be equal to 2. What do I want to calculate here? The same, delta at point C, which is delta C, and it's called delta 11 dash now. Delta 11 dash. It's only one force, which is downward, so positive 2 times 2/3 of the 2 meter, which is 1.33, divided by EI, which is 2.67 divided by EI. What is the condition? What is the condition? Is it delta at C? I am calculating delta at C in both cases, right? Is the delta at C, the vertical displacement at C, equals to 0? Is there any vertical reaction at the main beam? Is there anything making the vertical displacement equals to 0? There is nothing here at C that is making the vertical displacement at C equals to 0. So the vertical displacement at C does not equal to 0. So what will be the condition at C? What will be the condition at C? So every example will have a tricky condition, and the trick will only be in the condition. If you didn't get the right condition, so you'll not be able to draw the shear force diagram and the bending moment diagram. So you have to think about the condition for each example. Okay. Let's imagine this is our beam. The black part is called AC. The right part is called, or the red pen is BC, right? What will happen at the internal hinge C? It will move downwards like this, right? Nothing will stop it. So there is a vertical displacement at C. When you put a loading on this beam, the hinge at C will go down, right? So what will be the condition now? Will it go down like this? Or each part will go down like this? They will move together. They are a stable structure. They will move together, right? This will not move by itself, and this will move by itself like this. If this is the real thing, so they are unstable. So the stability means that when they move, they will move with each other like this, right? So the condition will be delta C for AC equals to delta C for CB, right? C will move the same displacement for both of them. What is the delta C for AC? It's delta 1 node plus x delta 1 1. What about the delta C for the right part BC? It is delta 1 node dash plus x. Yeah, the same x. The same x. It's not x1 and x2 because it's the same redundant R. They are equal, right? Delta 1 node dash plus x times delta 1 1 dash. This will be the condition. And here the same for EI, the left hand side will have the same EI down, and the right hand side the same EI. So I can remove the EI from the whole equation. And from here, x will be equal to how much? 3 point? It's here 3.78. 3.78. 48 minus 10.67, yeah. And the other side will be 0 plus 2.67. Yeah. No, no. It's just, I will leave this more than enough. If it's wrong, so it's okay. You can double check. 3.78 tons. What is positive? What does positive mean? What was any positive mean? That the assumption is right. What was the assumption here? Here was the assumption, not here. Here was the assumption. So this assumption is right. Positive mean that it is right. How can I draw the shear and bending moment? You will draw the shear and bending moment for each part. For each part. So for AC, now you know that this reaction is 3.78 and here it is 3.78 as well in the opposite direction. Now we can calculate the reactions for each part individually and then you will draw shear force diagram and bending moment diagram for each part individually.